Okay, I'd like to introduce our excellent speaker of the evening. He is the Principal Solution Architect at DataStax, as well as the Chief Evangelist for Apache Cassandra. Please welcome Patrick McFadin.
I just had to take a quick picture to prove to my boss that it was working tonight. Because he's always like, how come I always get the bar bill? Are you really doing stuff? Dude, these are all my friends. Live from New York, it's me. I just came in today. So I'm here for the Strata conference. Is anyone doing Strata this week? Whoa, database team group here. Only 2 hands? 3 hands? All right. Well, I was going to say we have more t-shirts at the booth, but you won't be there. I'm Patrick McFadin. I'm mostly Chief Evangelist for Apache Cassandra, which is the open source side. I work for a company called DataStax. We are the enterprise Cassandra company, kind of like the Red Hat to Linux. And I've been doing Cassandra work for 3 or 4 years now, actually 4, I've counted, which is a long time in Cassandra years. It's like dog years, because it's only been around for about 6 years. So how many of you use Cassandra now? How many of you want to use Cassandra? Excellent, right on. Well, this is what I've done for years and what I still do from time to time. DataStax, if you need help, let us know. Jim's in here. Raise your hand, Jim. Jim is one of the people from DataStax, can help you. But if you need professional help, and not that kind, you need professional help with your Cassandra installation, that's what we do. But tonight I'm going to talk about Cassandra and Spark. And on that note, Cassandra, so the funny part about the Cassandra thing, the trivia question about the mythology thing, which was really funny because I never did Greek mythology, even when I was in college. But I wound up reading more about it. And it's actually a pretty tragic tale. Avinash, one of the guys who invented Cassandra, thought it was really funny because he took one little line out of some Wikipedia page and said, that's what we're going to name this database. And it was Cassandra foretold the doom of the Oracle, but no one would believe her. Now, if you read the rest of it, it's pretty bad. Like, Apollo wanted her to be his girlfriend, and she's like, no. And pro tip, if a god says, be my girlfriend, do it! Because he pretty much cursed her, and she had a horrible life. And then when people start reading all that, they're like, why did you name your database that? It's not my fault. But, so now at the end of Greek mythology. So let's talk about a couple more things. How about some technology? So what is Cassandra? So if some of you are using it, you probably know what it is. If some of you want to use it, maybe you'll need to know this. So this is a database. Pretty boring database, really. And the reason I say it's boring is because it just doesn't break very easily. And it's the most important thing in your infrastructure is the boring thing, right? Because that's what's not going to wake you up. It's a shared nothing architecture. It's masterless, peer-to-peer. That means there's no elected leader, no master node, anything like that. And it's based on the Dynamo paper. I'll talk about that in a minute. But this is really what it's about. It's a shared database. It's all about scaling. It's been proven over and over again. It's kind of almost boring, but it's still cool. The original plan with Dynamo and then Cassandra was that we would want to make this linear scaling. You want to make it so when you add more nodes, you get more capacity for storing more data, for inserts per second, reads per second, how many operations per second. And you can scale this up to millions and millions of operations per second. And that's pretty cool because capacity planning is hard, really hard. We were talking about some Oracle. I was an Oracle DBA for 15 years. I got paid a lot of money to guess. It was awesome. Yeah, we're going to make it through the next season? Yeah. Let's buy the biggest box HP will sell us. Okay, let's do that. And that's how we did capacity planning, right? You just bought the big machine. I mean, I bought a 6U server and installed it and walked away thinking, man, I hope that's enough. And actually, it almost didn't turn out that way. What I really could have used is to add another node. That would have been a lot easier if I just added capacity. So if you hear use cases for Cassandra users, that's what they do. Like Netflix likes to talk about this a lot. That when it comes time for everyone to watch TV, They start turning it on, things start ramping up, they just start adding nodes to their clusters to get more capacity. That's a great way to do performance planning, is not to plan. Just have a plan whenever you need more capacity. Uptime, one of my favorite things because I like to sleep. I worked in ops for a long time. I had a pager. It kind of looked like this, right? I know, it kind of dates me, right? But what did that mean? And then we moved to just text messages. 3 o'clock in the morning. That's when every database goes down, right? 3 a.m. And that was really a bummer because you had to get up and deal with it. There was no stopping. And that meant that single point of failure has just turned out to be a really big problem. So my first experience with Cassandra in operations and having a bad day was brought to us by our good friends at Amazon, who just gave a lot of people a bad day recently. Anyone survive a reboot? Oh, yeah. Thanks, Amazon. They do that as a service. You paid for that. So I like to say that Amazon invented Dynamo because they knew how shitty their hardware was. And it's true, right? Because Amazon stuff goes down, and every data center goes down. And you don't want to have a situation where one event is going to bring you to a screeching halt. You want to be able to maneuver around it. So my experience was I had a bunch of nodes of Cassandra running in Amazon. Amazon 1C went down on a Saturday. Buddy of mine at Instagram was flipping out. They were having all kinds of trouble because they had all this storage set up on EBS, and they were trying to get it back online. I didn't know about it until Monday morning. I came in, hey, there's some gray nodes. What are those? Oh, 1C went down. That's weird. Let's boot them back up and we'll find a place to put them. Application didn't go down. Didn't have any failures. Users didn't see it. That is really cool. I tried to make Oracle do that for years. And that's really hard. Costs a lot of zeros, right? But this is what this database is designed to do first. And that's a cool concept. So this graph right here, this really, really big graph that you can't read any numbers on, that's good. This shows like this is one of the features of Cassandra. It's called rapid retry protection, or eager retries as we originally called it. And this is all about your nodes protecting themselves. So we took out one node during a high read. These are 40,000 reads per second across a medium-sized cluster, or a small cluster, really. It's not 75,000 nodes. And when we took the one in the blue line, the one that's dipped all the way down, the other ones react by maneuvering the traffic around it. The application doesn't know about that. And that's what you want. That's what you're trying to build and architect your product to do. Here's a great saying. You use Oracle whenever you want to count your money. Use Cassandra when you want to make money. Drop the mic. Or the clicker thing. That's kind of nerdy, right? You know how nerdy I am? I have my own name badge. That's right. I come pre-installed. So the Dynamo paper, 2007. It's one of those papers that just hit, and everybody went, whoa, really? You can do this? I read it in 2007. And it was about this problem. Amazon had this problem. We need to make sure that our shopping cart is online all the time. They're using a lot of Oracle, MySQL. They can't do that because there's a lot of single points of failure. They have routing mechanisms and ways to cache around it and whatnot. But it was very expensive and very difficult, and they couldn't route this geographically. So the Dynamo paper was about how do we do this in a consistent way, because this is our money. Amazon's shopping cart took $4,000 a second. If it's down for a couple of seconds, that's money. That's serious money. So a couple of seconds, that's like nothing. But it is, it's something. And if they're down for an hour, don't do the math. It'll scare you. So this is what the Dynamo paper was about. What was interesting, and I liked about it, because I'm a computer scientist, it cites real computer science. It wasn't a crazy dream. It wasn't some mad scientist coming up with something, or worse, some hacker kid in a basement. More cheesy poofs. Wasn't any of that. It was real computer science. And they cited papers on back to the 70s about quorum and consistency and things like that. By the way, quorum, that means 51% of your nodes, of your replicas are online. That's where that number came from. I'll cover it in a minute. But the Dynamo paper inspired a lot of things. There was REAC, Voldemort, and Cassandra. those three. There's also some other technologies that are Dynamo-based as well, not especially databases. There's some cache technologies that are like this, because it really just kind of nails the idea of having a distributed system and a database. So I'm going to talk a little bit about time series. Because time series, for me, is one of the more interesting things about Cassandra and the problems that we're trying to solve now. You know, I listen to a lot of use cases, and blah, 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 blah. It's a temporal-based data problem. Time series is our new problem that we're trying to solve all the time. And it's not just the only problem, right? You still are collecting money, but a lot of times it's about ledgers and where your users are on your system, and a flight recorder, and knowing what's going on. It's about what's happening now. You need to know what's going on now. Because if you don't, your competitor is. And your competitor is probably going to beat you to the punch, and you're going to lose out. Amazon figured this out. You remember that study where they showed that like for every 1/10 of a second they took off of their web load, they made $1 million or something? They figured that out. And that means that speed is king. So that data now is the new currency. You know, I have a Nest, you know, the thermometer or the thermostat. Google paid $3 billion for that. Now, you think they were Google? And they're like, yeah, dude, we got this really cool automatic car, got this really great search engine. Man, you know what I really wish we had is a cool thermostat. No, they don't care about thermostats. They care about the data. You know what's an interesting feature at Nest? It knows when I'm home, and it knows when I leave. Oh, we got the NSA guys. Oh, yeah. So the NSA does too, by the way. That's something that Google knows now. Creepy, right? They paid $3 billion to get into my house. They got there. So data is a currency. They're going to be able to use that data somehow. And I hope it's for my own good. All right. So why Cassandra for time series? I mean, there's plenty of ways to store data, right? Well, it scales. Seems like we've got a huge problem on our hands here. Let's face it. We're not storing less data. It's pretty resilient. It stands up to a lot of abuse. When your thermostat needs to tell Google that I'm home or not, they want to know. They don't want that downtime. That's a pretty good data model. I'll show you how that works. But there's something else that it does, which is really, I think, a fundamental of how Cassandra and time series works. And that's a sufficient storage model. So what about that? Let's talk about that. And if you're used to storage models and say like in other databases like MyISM or Oracle DB format or Berkeley DB file or SQLite when you really want to get serious. This is a different type of setup. So let's walk through an example. We're going to go through a weather station. So a weather station, simple temporal data model, right? We're collecting weather phenomena or weather data and storing it in a time series. So weather station collects the data, we put it in sequence in a Cassandra cluster, and then later my application will read it out. You know, this is just, I think I took this right off of Weather Underground. I should have put a link on there. But yeah, this is what we expect to see, like a little graph, right? And that's time series. It starts at one time, it goes to another, and I get temperature on my axis. Great. Well, how do I collect that? Well, when you do any type of Cassandra work, this is how you start. This is where you start with your data model. And how you data model with Cassandra is you start with, it's really query-based. So we want to look at the queries. So what do we need for queries? Well, we want to get all data for one weather station. We want to get data for a single date and time. And we want to get data for a range of dates and times. Range data would be like that graph. So the data model that we're going to use to support that, so we want to store data for one weather station and store it in a time series from first to last. So first thing to happen to the last thing to happen. So let's take a look at that. Now this is all of you who said CQL, here it is. This is CQL, Cassandra Query Language. It looks pretty familiar, doesn't it? It's very familiar. It's meant to look familiar. And it's meant to do the right thing on the storage engine, and I'll show you why. So when you create this table, temperature, I have a weather station, that's the ID. You know, every weather station in the world has some sort of an ID on it. And then I collect my year, month, day, hour. That's the time portion. I'm collecting it every hour. I have a temperature, which is stored as a double. And then I create a primary key. Now, before I get to the primary key, Did you notice anything here about this create table? Something that's missing that you might normally see in a relational database? Somebody say size? Size. Somebody said size. Yes, there's no sizes. I mean, how many of you can type varchar 255 in your sleep? Right? Just do it. There's no 255. And it's because Cassandra doesn't really care as much. Each column of data can store up to 2 gigs. That's a practical limit. Or there is a practical limit. That's the physical limit. But there is a practical limit. Do not try to stream 2 gigs of data into your server. You'll wait a while. But that gives you a lot of flexibility, so we don't really track sizes. Now the primary key here, and I'm going to go in depth in this a bit, but this is what shows uniqueness for this record. This record is the weather station, year, the weather station ID, the year, month, day, and hour. That is a singular event, right? And it should be. That's something that happened. And I'm just going to store the temperature for that. So these insert statements, you'll notice I'm grabbing 4 different weather events, 4 different hours, and I'm just inserting those in. This is pretty easy to do. You could do this tonight. So when I go to select my weather station and my hour and my temperature from that table, there's a typo, shouldn't have an ID on it. I just look for that one ID and I get all my hours here. Here's 7, 8, 9, 10, and then my temperatures, and then my weather station ID. That gives me a nice row and column layout. Very easy to do programmatically. Now, if you're a programmer, you'll love this. This is what you're used to. I iterate over rows, I get columns. Awesome. DataStax has a bunch of really cool drivers, and they're getting cooler every second. We just dropped GA today, our Node.js driver. That's right. I know. I see a bunch of hackers out there. Not really. But we have a Ruby one, we have Java, we have C++, we have C#, Python. Oh, don't forget the Python. And they work on this model. You get a row, you iterate over the rows, and you get columns. But what's interesting about this is what you see. Now, I mentioned this before. The storage model is the interesting part of this. The storage model is what makes Cassandra really cool. And let me show you how that works. And I have a wonderful animation for that. So what is actually happening here, this is how it's stored on the file system in a sequential format. Now, what we know, because if you do any work on disk, what's the worst thing you can do? Random I/O, right? Because that's just going to thrash the living hell out of your disk. And that's when you start finding those numbers, like random seek time, really hurt. You know, SATA disk, 7,200 RPM SATA disk, with 15 milliseconds, average seek time, 12 maybe if you're lucky. That means every random seek is going to take that long. That's not what I was looking for in a fast database. So when you store things in a sequential format like this, you're optimizing for what you have. And with spinning disk, that's a real problem. And with SSD, it's more optimized in the first place. Even with SSDs, they don't have a head that moves around on a physical head that has rotational momentum and other cool physics problems. But they do have this issue of being transport aware. So whenever you use an SSD and you get a single seek, oops, back. When you get a single seek off this, it's a lot faster. So whenever you're storing this data in this sequential format, whenever you add data to it, like I said, I'm just going to keep adding it to the end of that file. Now, eventually, this is what happens with your file as you add data to it, is you will get a long sequence of data for that one weather station. And it's co-stored on the same file. This is when your data finally settles. But this is more efficient. So why is that more efficient? So take a look at this. So what about the primary key, and how does that work in the efficiency? So I'm going to take a little diverge here. So let's talk about that primary key. What about that primary key? And I'm pointing out the primary key because this is the secret sauce. This is what makes that happen. So a primary key has these four parts. So weather station, the year, month, day, and hour. That's 5. Sorry, 5 parts. 4 parts included with 5 things. It's part 4 of a trilogy. So primary key, weather station, year, month, day, hour. That creates a unique record. But how does it break down? First part, that weather station, the very first part of the primary key, is what we call the partition key. that gives you locality. That means that gives you, that puts you on a single node. Now the rest of this is what we call the clustering columns. This is what says I want to put that data, co-locate that data in a single sequence in a file. So whenever I take my number here, my weather station ID, that's my partition key, and the clustering columns are going to create, see how they're clustered together? The dates are clustered together, and they're stored in order on the disk. In order, sorted, merged, ready to go. When you go to read it, it's ready for you to do. So what about this node locality business? So partition keys, very important concept. If you have a 1,000 node cluster, the worst than a random read off a disk is having to go look at all 1,000 nodes for your data, right? Hey, I would like this one weather station's ID. Let me go check 1,000 nodes and I'll get back to you. That's going to take a while. So an important way to get speed, the key to speed is getting locality. You want to just be on a single server. So that partition key is going to do this for us. So I have a couple of inserts here. And you notice that my primary key, I have these two partition keys. Those are weather station IDs. So they're down here, way down here on the left. So what we do with those is we run them through a murmur3 hash. And that hash creates a really big number. It's a really, really big number. It's a 128-bit hash. So that is a consistent hash, because it's murmur3. It's quick. But consistent means that whenever I put this weather station ID through the same hashing function, I always get the same 120-bit number. The fact that it's a 120-bit number pretty much guarantees you'll never get a collision. Now, unless you're a German PhD student, you probably won't argue with me on that. They do. There is potential for collision in the universe, but it ain't going to happen today or tomorrow. So this big number right here, that's what's really going on. For the sake of our discussion tonight, I've shortened it to 2 digits. Just makes it a lot easier, right? So in our make-believe hash, this weather station ID turns into a 15. This weather station ID turns into a 77. I can actually remember those numbers. So how does that work in my cluster? So this is how replication works, actually. And this is part of the Dynamo paper that is so elegant, the part that I love the most. This is so good. Because replicating data is hard. Synchronous replication will kill you, right? And if you're doing synchronous replication, it will get behind. You know, slave lag, hello, anybody? And you have to wait. If there's ACID properties, then you have to wait. Asynchronous is the way to do this. So how does this work? So when the client goes to write data, the client is going to write it to any node in the system. Now I have one cluster and 2 data centers. I'm giving you the full deal here. This is one of the first class things that Cassandra can do is multi-datacenter replication. Probably, if you're looking for a multi-datacenter replication technology, this is the only game. There's a lot of pretenders out there, but this is the only one mathematically proven to work the way it should. And probably why I picked it originally, because I needed that. So this is how it works. So we have 2 data centers, 4 nodes in each data center. So when the client writes to its own data center, random node, just picks one, and it picks this first node, that node's job is to read the data, take the data, but also distribute it to the replicas in an asynchronous fashion. Now once that they're put into those nodes, it goes back to the client, I got this. But that coordinator node's job is also to replicate it across the WAN. And just picks one node in the other data center. It's very efficient that way. It isn't blasting this parallel of data. It's just picking another node on the other data center. And then that node's job is to distribute inside that data center. So this is how you get very quick replication over the WAN. This is why companies like Netflix, Spotify, a few others. Oh, that camera's on. That's why they use active-active. Active-active is like the holy grail of distributed systems, right? I always had like standby data center. There are companies out there that do not have a standby data center or a second data center because the CFO said, no, you're not going to spend money on a data center that's just going to sit there and spin and not do anything. So why not have, if you're going to have 2 data centers, use them both. This is how you can do it, and this is done all the time. If you ever used Netflix, you do this every day. It's funny, because I'm on the East Coast now. I'll be using the East Coast data center if I watch Netflix tonight. If I go back to the West Coast, I'll be on the West Coast data center. And that's how they work. Now, we have this replication going, but now what happens when I go to read this data? So my data is distributed very well. So if you notice this RF of 3, that means I have 3 copies of my data in each data center. Well, that's pretty safe. I now have 6 copies of my data. Good to go. If I lose an entire data center, I still have 3 copies of it. If I lose one node, I have 2 copies of it. As we all know from the quiz, a quorum read is 2 out of 3, right? 51%. One node goes offline, still good. And trust me, that's a great thing whenever you want to reboot one node. When they did the reboot, our Cassandra users, pretty happy. Because as Amazon was as a service, rebooting random nodes, they're like, that's cool. Netflix has a great blog on that. They lost them like 280 something servers. Cassandra servers, 0 downtime. That's what I want. So what about the locality? So now my data is replicated all over. But let's go back to that key. So remember that key that I had was a 15. Remember I took that first weather station and I made it a token of 15. Each node is responsible for a certain range of data, primarily. And then it has replicas. So I have this table down here. That's what this is about. So I have this first node, the 10001. Its primary range is that 0 to 25 token range. But it's also stored in 76 to 100 and 51 to 75. So it's storing 2/3 of the data in that cluster. That means that if one of these goes offline, that out of the 3, I'm going to have my complete picture of data. That's just the simple math of how it works. And this is why it's linear, because it only replicates 3 times. If I have a 1,000 node cluster, I still only have 3 copies of my data. I have a 4 node cluster, I have 3 copies of my data. So this table is showing you where the data would be if I'm looking for a certain token. Now, if I ask for, hey, give me partition key number or my token of 15, where is that? I've hashed this, where is it? It's going to be on one of these 3 nodes here, right? And that's how it works. This is locality. I'm not going to go here. That's probably not, no, 10.004 does not have my range, so I'm not going to go here to get it. I'm going to go right here to get it. And that's where my data lives. Now we're just talking about a single server. We're not scatter gathering. There's some systems that will have to go out there and look at every single node in your cluster. That would be the equivalent of a distributed system full table scan. Just go out there and look at every single node's worth of data. This keeps you from having to do that. That's why whenever you have 500 nodes or what have you, you can do this. So here we go. We've got this 1 node of data. Now get this. If I have a client in the other data center, same thing. That client's going to be looking at this table. It's a replica of this. The client goes to get data. It'll be in that local data center. It's not going to have to cross the WAN link to get that data. The consistency factor and all of that are figured into this. Different topic, different talk. If you want to learn more about it, I have plenty of talks on YouTube. But we can control that. That's programmatically controllable. You want to have full consistency, you can do that. If you want to have rather loose consistency, you can do that too. And a lot of times, it's up to you. I mean, and that's an important choice, but it's good to have a choice. Because there's some data you don't really care so much about if it's consistent within a few seconds, or maybe a few milliseconds. There's some data you want immediately consistent, and you can choose that. Physics still apply, though. Remember when you're crossing a WAN link? We're not breaking any laws here. You still get 70 milliseconds of LAN latency, WAN latency, but you can manage this. The companies that are doing it, everyone has figured out a plan. I can help you figure that out too. We got people here that can help you do that. And that's an important part of understanding Cassandra, is knowing what that is. It's called eventual consistency. Yeah, uh-oh. So I bring up eventual consistency, the hand comes up. Go ahead.
How can you have a different consistency
You can have a different consistency for the read and write. So how can you? Well, if I want to write my data and I want to be fully consistent, meaning that every single node, a fully consistent write means that every single replica, so that for that 15, that means these 3 nodes right here, every one of those nodes has to write it to disk and send it back saying, got it. That's fully consistent. Now, if I want to change up and say my read is just a read of 1, meaning I only need 1 of the replicas to give me a data, that's totally cool. Whenever you're programmatically, you can have different consistency levels on reads and writes. So if you want to, let's say that you have a really heavy read system. 99% of your systems are reads. 1% are writes. I'm going to make the writes heavy. I'm going to make it fully consistent. User authentication systems, there are plenty of them out there that are using Cassandra. The writes are usually pretty consistent or even locked with Paxos. But the reads, they're just a read of 1, because what you're doing is you're saying, I took care of the busy work, the front end, now I'm just going to read off any node that I can get at, because I want to get sub-millisecond reads. If you want faster than a millisecond, you're going to have to just do it on 1 node, because physics is a problem. So I hope that answered your question. Okay, so that's how you can do a combination of those. And there are plenty to pick from, too. There's different consistency levels you can work with programmatically. More consistency questions.
Just a real quick question. Does every node have a copy of the hash table, the token hash table?
Good question. Does every node have a copy of the hash table? Yes. Every node is completely aware, is topology aware, and it's done through a protocol called Gossip. And Gossip is the most misunderstood and least loved protocol, but it's so nice. This is how you get large clusters to talk to each other. It's not a Cassandra thing. It's the Gossip protocol. It's actually based on the epidemic pattern, which is an old computer science paper, which is a lot of fun to read because they pretty much take, I guess it's pretty timely, like this whole Ebola thing that's happening right now. Go read the epidemic paper. You'll understand it completely. But, sorry, did I say Ebola? Yeah.
So actually, it's on the previous slide where the data was inserted in the same order as the primary key. And then on the disk, it was like all stored in the same
This one?
order. No,
This?
Previous.
Oh, more back.
More back.
That one.
A little bit more.
A little bit more.
Yeah.
That one?
That one.
That one!
So here, basically, if I go and store in this, for the same key, for the same ways of operation, and I put like every hour, like what's the temperature, let's say.
Right, so.
It's going to be stored sequentially, so that when I do my read, it's going to be super fast. What happens if I insert things, but like out of order?
Out of order, okay. No, I'm glad, this is good. Now we're having a conversation. So, what happens if I put in, I did 7, 9, and 10, and then the 8 didn't come, like I had an API that blew out, and that 8 came along 10 minutes later, or like tomorrow. No problem. Because the way that this works is that primary key, there's a default sort order. These are all, if you recall, these are all integers. So that's the sorting order, integer. When you write data into a Cassandra cluster, it goes into a mem table. The mem table looks at the row data, merge sorts it based on the collating order. So this order will be withheld or upheld. And so when it gets written back out to disk eventually, it will be in the correct order. So you have that out of order only whenever there's no data. But it will sort in properly. It will merge sort. There's a more complicated process going into this. It's called compaction that happens later. If you write data later and there's a file already, it will compact those two together and merge sort them. So this is why you want to keep up with your compaction. It's important. But
So
that's still maintained.
So let's say I want to like write like a lot of data, and I've got the batch process that just regenerated my data. And of course, I've got a lot of machines, so I've got like 1 machine per year.
So this is a very common problem. Circa, who I'm going to go see next week in Sydney. Yeah, I'm going to Sydney. They do 2 million writes per second. They store every single trade in all the world's exchanges every day. They do 2 million of those a second. if you do 1 million a second, that's a write every microsecond. That's pretty fast, right? So 2 million, no, that's way faster than my computer. But they just have a really large cluster. And yes, you will get out of order writes, absolutely. But if you're using a sort order that's guaranteed by the primary key, it will eventually sort itself out, but first in memory. You just know that, hey, this is the order of things, and if it comes later, fit it in. It won't be random at all. It will be in order.
So following up on that, after it's written to disk,
Yes.
get an out of order written after it's written to disk. That's a compaction when it's not done that. Is that right?
Once this mem table is written to disk, it's never written to again. The SS tables, the files on disk, are never written to again. They're immutable. So the only way you can modify it is read 2 of them, put it in memory, merge sort it, and then write out a brand new one. Hey, mutable state is hard, right? Don't do mutable state. So you do immutable files, you reread it, create new state, right? We learned this with Erlang. Thank God I didn't program it, but I learned that. That's how you get things right. You keep them correct. All right, I'm going to move on because I got more stuff to talk about, but there will be Q&A after, I think. Yes, there will. Let me catch up. We'll see, where were we? We're talking about Cassandra, replication's awesome, consistency is amazing. Oh, look at that, I'm still replicating data across my way. Okay, and then I get my data. Okay, we're back to this, okay. So, now we have data that we need to get. And we're back to this data that's now fully sorted on disk. What about this situation now with query patterns? Whenever we have like a greater than or less than, I'm back to my weather station model. I want to get, and this is actually one of the things that makes a disk life really efficient, right? Is that whenever I want to get a range of data, which is pretty common, right? That's our graph. I want to see all these numbers in a series. So I'm going to grab everything from hour 7 to hour 10. Well, to do that, instead of doing a bunch of random seeks on disk, I'm going to go for the partition key to get locality. So now I'm on one server. I do a single seek on disk to get that one item. And then I'm going to do a read across the disk sequentially, which doesn't count as a seek. Then the magic in CQL is it all comes back in these row and column. Not for a programmer. So we just did this whole like boing, jumped over this thing. If you're a programmer, everything I just said for the last 20 minutes is irrelevant. Because this is what's cool. Oh good, I set my data in there, I get my primary key right, boom, there's my data, man. That's all you want. So look at that. That's what I wanted. Now, all that stuff that happened underneath, now back in the day before we had CQL, I had to teach people how to do that kind of stuff. That was like writing assembly language, man. It was hard. Now, thankfully, we have CQL. It does it for you. But this is where I take a pause. So your data model is really important. So get your data model right. Oh, programmers like this. So switching patterns. So let's switching a little bit, tiny bit. I want to talk about probably one of the most exciting new things that's happened in distributed computing in a long time. I mean, I don't get excited about a lot, well I do, but some stuff. I'm a distributed computing nerd. Cassandra was really exciting, but it's getting kind of dull. You know, it's like, oh, it's the same database every day, right? It's not, actually. It's pretty cool. Cassandra's moving really fast, and that's good, right? Because this database is growing like crazy. So many people using it. We just released 2.1. 3.0 is coming. I went to the committer conference on that. A bunch of us in a room just trying to figure out what we're going to build for the next thing. It's going to be off the hook crazy. I'm really excited about that. But the thing that's really exciting to me right now, that you'll see me talking about a lot, is Spark. Spark has changed quite a few games. If you've read the press, there are people like Mike Olson, Doug Cutting. Doug Cutting, he's the guy who invented Hadoop. Like, yeah, Spark's pretty cool. Mike Olson said Cloudera is moving to Spark. The MapReduce is dead. How? The machine learning from Apache are no longer taking the MapReduce. They're not doing any algorithms of MapReduce. They're only doing it in Spark. So it might be a good career move to learn Spark. So let's learn a little bit. What I feel is an interesting twist in this is what it changes for us, the users. I'm a user too. I wrote code. I wrote code on the plane today to show some of this stuff. But here's the problem that I've been trying to get away with. Right? Yeah. So the other part of my life that I'm not so proud about. But I ran a lot of Hadoop in my day, and it was really cool, right? Because it did everything that Oracle couldn't with a lot of shitty hardware. And boy, did I rack up a ton. I was like, wow, there's my old Oracle box. What are we going to do with that? Let's make it a Hadoop box. All right, let's do it. So Hadoop served its purpose. Don't get me wrong. It has done quite a bit. But when I talk about Hadoop in general, I'm not talking about just MapReduce. I'm talking about the ecosystem. How many of you run Hadoop in production? Oh yeah, there's some tired eyes out there. It's crazy town, right? It's really big. So it's a lot of overhead, it's batchy, and I want to help you get out. I thought this was kind of appropriate since I'm in New York. All right, so it is also somewhat inflexible. So let's get in there. So here's word count. I don't know, this is like hello world for Hadoop, right? Let's count some words. That's word count. That's, I can see the line numbers. 63 lines to count words. And that's just, and, I mean, come on, that was way cooler than what I used to do, right? But, you know, you have a reduce and a map. That's what you get, right? Because it's map reduce. And you had to set up a lot of hardware. You had to have Zookeeper running. You had to have your task trackers, your job trackers, your HDFS stuff, your region servers, maybe Uzi if you want to have job control. Yeah, I ran this in production. So all these things are in orchestration. And if any one of them falls apart, no more batch. We got to go figure it out. So what do we need to do? Well, scheduling gets you so far, right? That's what we do with what we did with Hadoop, is we scheduled. Here I'm going to, right back in the mainframe days, right? Well, we're going to let that run overnight, and we'll get some output tomorrow morning. Come in. Ooh, there's a really big error. And it's all in XML. Well, we'll do that tomorrow night. So we want stuff now, right? We're kind of impatient. And so companies like Teradata jumped on that. They're like, oh, wait, you don't need that. You just need to buy this really big machine. We'll do it right now. And what's more important to me right now, and I told you about time series, is what's happening right now. The event stream. What's going on now? Because when the boss says, man, did we get any customers today? Hang on. I gotta go run a Hadoop job. I'll be right back. Let you know in the morning. No, you need that on a plasma. You need to see that up on the, when they walk in, the boss doesn't even have to talk to you. He looks, oh yeah, that's what I wanted. So these are event streams. This is where a lot is going, right? You can see it right now. The event is what we have to capture. And we need to analyze it. So running computations on event-driven stuff is hard. So here's Spark word count. Let's talk about that. It is super tight. Now, it's Scala. I don't know if a lot of you are Scala writers out there. It's not super popular, but it is pretty popular now. It's a functional programming language, and it's running in the JVM, which is good, but it's very, very quick to write up these things. This is word count. Say, give me, from a Spark context, that's what this is. Give me this file, split it out, do some work on it. So, oops. And reduce it, and then save it back out again. It's just that simple. I mean, it's meant to be very quick, but how does that pull together? Well, Spark is not a new thing. So what they did at AMP Labs, and this is UC Berkeley, and they said, you know what, because it was in 2009. So at that point, Hadoop and MapReduce had been out there a long time. Well, let's say MapReduce has been there a long time. They got the benefit of being like the Monday morning quarterback. So that's not the way I would do it. What I think we all knew is that Hadoop was really thrashy on the disk, and Shuffle destroyed your network, right? And those two things alone created a lot of havoc inside your MapReduce framework. So they moved to eliminate that with some really interesting ideas. Quickly went from AmpLab right into Apache, my favorite place to stick your code. And now it's a top level project. It just came out with 1.1. If that's a mark of maturity, I'm not sure. But it's moving really quick. I was just at the Spark Summit in San Francisco. Just tons and tons of people there. Next year it'll be twice as big. And I was talking about Cassandra. So it's really easy. It's 10 times faster on disk, 100 times faster in memory. So guess what? It really likes memory. It's good on memory. So when you're running something that's close to a memory workload on that, let's face it, that's where the speed is, right? It works on elastic MapReduce, so if you're in Amazon, good to go. It uses these fault-tolerant data sets, so if you don't lose a job tracker and have to restart the whole thing, it's fault-tolerant. Fault tolerance is something I'm obviously into because it's Cassandra, but you need to have something that can just keep going, especially if you're looking for your data now. So this whole in-memory storage and disk stuff is really fascinating, but I mean, when you talk about speed, that's important, but also speed to getting the code out. Less code is going to make you more productive. So you can get started right away. There's a Spark shell, which I think is actually kind of fun to play around with. You can start it up and start analyzing data. It's not SQL Plus or anything like that, but you can write some code really quickly. And there's plenty of language support. So if you're not into Scala, there is Python as well. And there's a Clojure connector coming soon too. The API, I think, is probably the biggest change, right? We had two things, MapReduce. Map and reduce. So now you get a ton of really useful things like a join, a group by, a sum. Things that I had to do in my own code now are built into it. And the reason it's built into it is how it works. Because it's doing this whole business of filtering out your data and running it in parallel. That's, just like I showed you with Cassandra, the key to speed, data locality. You take a chunk of data that's common to each other in a locale and iterate over it. And that's what it's done. So that's what we call an RDD, resilient data set. So it's resilient because it can fail out, it saves a state, and you can go on, and you can move it to a different server. So you can get into, there's a lot of theory behind this, but basically what you're doing is you're massively parallel processing in memory. And you're doing it in a much more efficient way. So my favorite graph, it's just stupid fast. And I've seen this over and over again. I think that's where I see most people get excited, is it's just a way faster way of getting the job done. Yet we always have to analyze data. It's not just store it. You have to analyze it too, or else it's not going to do much for you. And when we're talking about real-time analytics, when we're talking about making decisions quickly, it's got to be fast like this. And the more memory you put into the thing, the faster it gets. So caching is a very important part of this. And let's face it now, memory is about the cheapest thing in your server now, besides the fan. Because maybe I got those gamma rigs with a really nice fan, blue light on it. That's pretty cool. Memory's a little more expensive. But memory's cheap. I mean, it's really, we're seeing servers getting pumped out now with 256 gigs of RAM in them. That's a lot of memory. I will never have to reboot Windows again. Oh, I don't run Windows. It's compatible with a lot of cool stuff. Well, right, HDFS, not so cool. Parquet, which I just like to say. CSV, everyone's favorite format. And, that's right, it runs on Cassandra. That's right, Snake has a Cassandra shirt. Who has a Cassandra shirt? He's got one of the originals. So it runs on Cassandra. Now when Spark, when we first started doing Spark on top of Cassandra, I had a guy, we were doing an event in Silicon Valley, San Jose, and this guy was pissed off. You cannot run Spark on Cassandra. It's for HDFS. It's built for HDFS. What are you going to do? I'm like, I wish I could prove it to you. Oh, wait, I can. It's not a replacement for just MapReduce. It's a whole new compute framework. And running on top of Cassandra, I'm going to try to show you this. This is where my excitement comes from. Is we built something here, and this is just serendipity. This just happened. This is so cool. It wasn't like the Spark guys got together with the Cassandra guys and said, hey, let's make our stuff work together. It just happened to work out really well. So it's a great combo. You know, toast and butter, as if you're British, or chocolate and peanut butter. Those are good combos, right? That's what we're seeing, is this is a killer combo. They're both really super easy to use. Setting up a Cassandra cluster is not hard at all. You can go to Google and hit one button. You can build a cluster in 10 minutes. Spark's just as easy. You can bridge your old Hadoop systems with this new paradigm and still hold on to both sides as you go from one to the other. And this Spark libraries, they're just getting going. I mean, it's amazing how fast this is. This is our Spark Cassandra connector. So Spark on Cassandra. Now we are making this work together. So you have these server-side filters that look at Cassandra data, where it is. So now that you're all Cassandra experts, you know, hey, data locality, those sequential data sets, that's really good stuff. You can do these cross-table organizations. Now, when you run Spark and Cassandra, the things you couldn't do before because Cassandra won't support those, which like joins and unions, now you can do. And the speed, because Cassandra's already pretty fast, you can, not even a fair comparison, but Cassandra versus HDFS, okay. Millisecond versus milliseconds. So I'm harsh on HDFS. It's a rock solid USB key of a file system, but I just never really relied on it for any speed. So, and then with the time series stuff that I've been telling you about, it's like, hey, this is what I need. Because not always do I just need to grab a slice, right? Let's face it, we got to aggregate some of that data. It's got to happen. And so what we found here, we just took out the HDFS part, put in Cassandra, everything up applies. So if you love Spark SQL, no problem. Like Shark, Spark Streaming, got it. Graphics, graph libraries, machine learning stuff, all there. Good, good. Because it's talking to Spark, and Spark's talking to Cassandra. Completely abstract. It's awesome. And whenever you run it in an analytics workload type situation, this is where it really gets interesting. So DataStax Enterprise, our Enterprise Edition, you can download for free, 100% free. It runs Spark. You can download it and be running in 10 minutes. There's an installer, runs on Mac, runs on Windows. You can have Spark running on your system on top of Cassandra within 10 minutes. If you got fast internet. If you got slow like me, it's only 15. But you can have it installed and ready because it's installed in DataStax Enterprise now. There's ways, and it's fully supported in open source as well. We have all the connectors in open source. But if you want the integrated package, use DataStax Enterprise. And if you want help getting it working in your, like at work, that's where you want to talk to us. So how does that work? So the connector itself, it's all about data locality. I have just told you about how, and we're wrapping things up here, almost done. So we have this key to speed, get data close to the disk, right? Get it on that single node, do that sequential read off the disk. There's this node first load balancing policy. That's built into the Spark connector. It looks for the correct node where your data is and only reads that data from there. So when you're running this massively parallel job and you have 500 nodes, it only goes to those nodes and runs the computation off the nodes that has the data that it needs. It chunks up that task and puts it right on top of the data. So when you're running Cassandra and Spark, you run Spark on top of Cassandra, the same node. That Spark instance is aware of what data is underneath it. That can make it really fast and it can really make it scalable. So this whole locality thing is what we take advantage of because it's just built into Cassandra. We're building it into Spark as well. And Spark really flies. I don't have any graphs, but it's like 40 times faster or more than HDFS. So that 100x speed that you got, put another 40x on top of that. You know, Databricks just did their 1 petabyte sort in Spark, and it took 23 minutes. we were talking about, let's do this on a Cassandra cluster. Let's see how fast it'll go. We can break some rules. So I'm not, when you get into this key to speed thing, we're going to go down to this index. We're getting it down to that SS table. And this is where that sequential layout that I just showed you on the time series works out. And I have an example on that too. So this is what's cool about this. You can make a Cassandra table a Spark RDD. So you have data already in Cassandra, or you're ingesting it at speed, millions of writes per second. You can put a Spark RDD on top of it. So basically, you can analyze that data in place. That's crucial, because if you've ever done ETL, you know that kind of hurts. Moving data hurts, because when you have to move a petabyte of data, it takes a while. You want to analyze it in place if you can, and use it in place. So you can read data from Cassandra, analyze it in memory, push it right back into the same Cassandra instance. That's pretty cool. So we can map a table to a Scala object, which makes it really easy to iterate over. And it does all the server-side selection. So it pushes out those functions because it's Scala. It'll push those functions directly to the server, run it on the server, that code on the server, on that local data set. So whenever we have this thing called virtual nodes in Cassandra, which breaks the server into 256 smaller chunks, it's actually even faster on that because you have these little smaller iterations now. We map up really well our types. Remember we had the varchars. We map the types pretty well against Scala, so it makes it easy. And here's a diagram that shows how it works. So a Cassandra row goes to tuples and then back to the table. So the table and the row creates the tuples back into the table. It's just a really quick iteration, all in memory. That is amazingly fast. And so whenever you create this, this executor knows where to put the data in it because it's locality aware. So as these tokens, those 128-bit numbers, it's aware of those tokens and it knows where they are. So when you say, hey, I want to analyze this one weather station's worth of data, it puts that code over there to analyze just that one weather station's worth of data, just on one node. And by co-locating, and I'm reiterating this, but this eliminates the network hops, the shuffle problem. This is the big one in Hadoop. Like 5 years ago, there were some guys, one of the first stratas from Yahoo was talking about how they were using this new 10 gig networking everywhere to deal with shuffle. So this is not going to be a problem. So let's look at how we work with this. Super simple, and it gets simpler. Hang on. This is how you connect. This is some Scala code. You create a Spark configuration. You connect here's your Spark node, and then you set up the host. In this case, they're the same. A username and a password for Cassandra. You have a new Spark context. And so you're gluing your Spark and your Cassandra in the same configuration file. Now, when you have your resilient distributed data set, it is now sitting on that table from that configuration. So it's immutable, right? That's good. And as the data comes in, it'll change. It'll reorganize. But it is that partitioning. So now, whenever I do my transformations, like my filter, map, distinct, that sort of thing, I'm doing it on a Cassandra table. So in this case, when I do my, my word count thing, that transformation part, instead of being from a file, is actually going to be on Cassandra data. And when I do my action, when I collect, I bring it in, now I'm going to actually put it on the Cassandra table. I have a quick example for that. So I'm going to create this really simple table here, where I have my word count, and I have a bar and a foo, one's 30, one's 20. So I create my RDD, which is for my, this is the key space and the table, and I just do a for each, and I print them out. And this is what the printout would look like. But then I get the column names, the sizes. I'm actually reading data right off of the table. I can say, give me all the columns in that table inside Spark. And I can grab the first row, and I can do a count. I can do the integer of the count for that first row. Now what's interesting is now I can save that data. I can put these together and save them right back into the Cassandra table. So I'm doing my aggregations in memory. So now when I'm done, you'll see that I got that data, the 40 and the 50 inside here. So back to my weather station. Let's say I want to create a badge on my weather station. Now this is like, this is the big finale. This is where I'm going to loop you back. So you collected all this high-speed weather station data. It's coming in fast and furious. Now I want to analyze it and I want to put it on my website. So I have my, I want to have the badge that shows the high temperature and the low temperature for a certain day, right? Well, what I'm going to do is the weather station is going to put that data in Cassandra, but then Spark's going to do roll-ups. I'm going to create new data from old data. So this is how I'm going to do it. I have a new table called daily high-low. Here's my weather station again, and a date, and I have a high temperature and a low temperature, and then what this shows is that I'm going to make weather station and date. Notice how I put them in parentheses like that? That means that that one value is going to get hashed. That's going to be my partition key. I'm grouping those together. So that's unique on disk. So I'm using Shark here because that's a really simple way to explain it. Shark runs on top, is the same as Hive, where Hive is to MapReduce, Shark is to Spark. So, and now Spark SQL is out. It's not fully in GA yet, or it is in GA, but Shark is still pretty prevalent right now because it's Hive compatible. But I just wrote this really quick. Now, insert into. How many of us have done that on a relational database, where I've created a new table based on a join of another two tables, right? So I insert into this daily high-low, and I do a select. And I'm grabbing, I have a function that will combine the year, month, a day, and hour and turn it into a date. I take a max of the temperature and the min of the temperature. And this is the interesting thing. I do a group by. I'm doing a group by down here where I'm grouping it by weather station, year, month, and day. So I'm saying, here's a unique day, give me the max and the min of that day. Insert that into a new table. When I run this, and I ran this on my laptop on I have a weather set of like 30 million records. It took 2.3 seconds. Now granted that was cache because I ran it the first time, but that's pretty quick on my little MacBook Pro. And that is really compelling. Because now I don't have to really think about my data too much in the first pass. I can aggregate after. So what just happened? I took that table data, temperature, read it, transformed it, inserted it right back in. All in place. No, it didn't move it out of the system at all. So I can do other things too, like histograms. Oh yeah, I got that. I'll create these nice tables. So these functions, really complex functions that are built into Hive and now Spark SQL. Now I can do those analytic functions on top of Cassandra data, which was never possible before. So you can see why I might get a little excited when this kind of stuff is now easy. The easy button is here, and it's super fast. Oh, and it's resilient. Oh, and it scales. Wow. Those are all things that we've been promised before, right? I've seen this show. It didn't end well. But we're starting to see this more and more. There are more users using Spark on top of Cassandra to do this. Just recently, the guys at the Weather Channel, and there's nothing to do with my data model, the guys at the Weather Channel just published a blog post about how they're doing this in production, using Spark on top of Cassandra. And boy, it caused a lot of fury. I loved it. If you could go on Hacker News, it was a total Hacker News fight. Because all the MapReduce guys came out. No! But it's the way it works, man. So this kind of ends everything. I have the word question on here, but hold on. David has to do something first. If you want to know more, if you want to follow me on Twitter, please do. I talk about this all the time. That's all I talk about. Nothing else.
Before we move on to the Q&A, I first want to give a great big round of applause to Patrick McFadin, Chief Evangelist for Apache Cassandra. And let's take the first question. Who's got the hands up? There's a bright light in my eyes, so you guys got to raise your hands up way high.
So the time series data you were collecting was kind of pretty sequential. What happens if your time series data is more like sparse and clustered? So like, let's say we're monitoring like server traffic, and sometimes your server is very busy, and sometimes there's no one on.
Yeah, it's bursty.
Yeah.
Yeah, I mean, yeah, So I've built, I'll give you an example, probably it's right on what you're talking about. And this was a very public use case. NASA Ames, they have a supercomputer there. They're using Cassandra to collect all of the stream traffic into the cluster for security reasons. It was basically a big flight recorder. Now, that's bursty, right? I'm going to type something, and I don't. Then I'm going to upload some data, then I don't. So that data wasn't a steady weather station like that, right? It's still temporal, though. Everything had a timestamp on it, and everything had an order. So there are a few things to consider when you're talking about time series, and that is how much granularity that data is. Now, I mentioned if you're doing 1 million writes per second, that's every microsecond. Okay, every microsecond has a piece of data. Most computers don't deal with microsecond, 1 microsecond. They do a few. A context switch on an Intel chip currently is 10 microseconds. So within a context switch, you lose 10 events. That's bad, okay? So, yeah, I love South Park. So what can we do to fix that problem? There's a type called a time UUID in Cassandra. UUID. Right. And what it does is it takes the time down to nanos and also has a UUID component on the end of it. And so, and it's sortable. So the time portion of it, based on nanos, is pretty good granularity, if you believe in JVM Nano and Easter Bunny. But it's pretty close. But that UUID, so you have potential for collision in that bursty traffic. This will keep the collisions from happening because now they have a UUID on it. It's still sortable though. And you still have that need to have it in some sort of a pattern. And that will guarantee it. Yes?
I actually have a couple of questions, but I'll just ask one now. Have you used, I guess with Spark SQL, we're trying to do like a little POC, and we want to do like real-time streaming, not a million inserts a second or anything like that, but we kind of want to do some aggregate real-time streaming to kind of show what our customers are doing across our system.
Right.
Have you seen that in use? With Spark SQL, or should be Shark, or performance of that? Is it just a matter of scale? The more memory you have, the better performance you're going to get?
Well, actually, the reason I'm at Strata is to do a tutorial tomorrow, 3-hour tutorial on using Kafka, Spark Streaming, and Cassandra.
That's how we're doing it.
Yeah. So they only had a room for 30 people, so it's sold out. But I'm going to put all this out on the web. So that's the coming attraction. The reality is yes, and Spark Streaming is really, so there are some things you should know about Spark Streaming versus, say, Storm. Storm is tuple-based stream analytics. It's in the stream. Spark is micro-batch. It takes a chunk, does the analysis, deals with it. So it's a very subtle difference that you have to understand what those differences are. That being said, it works well. Think about RDDs. Composable data set, iterates over it. That's how it works. So that's where your real-time analytics are going to come from. The example that we're going to be doing is on this weather station. I have billions of records, and we're just going to stream it into Kafka, and it'll start pulling events off, and it's going to do real-time high-lows during the day, cumulative precipitation, just things that you wouldn't want to have to go back and analyze later. It's just doing it in stream. And it's saving that data out to a Cassandra table and forking it, basically. Storing the raw, and then the aggregation. So you're creating a lot of materialized views in that case. That's the nutshell. Yes?
Hey, so I'm a data scientist, not a systems guy. My question is, if you run Spark and Cassandra on the same cluster, how does the analytic loads from Spark affect Cassandra performance?
You could be an ops guy. You don't have to be a data scientist all the time. You could be an ops guy with that kind of a question. Real quick, I showed you, and I didn't even mention it. The reason that, all right, so this little bit right here, because Cassandra is topology aware, it knows each data center is different, you can create, and it's all one data set because it replicates fully across the cluster. So you create one cluster, 2 data centers, virtual data centers. So the one on the left here is just Cassandra. It's now running Spark on top of it. The one on the right is Cassandra with Spark running on top of the same data. Now, I could look at all the nodes that I have over in the Cassandra side, and look at all the nodes I have on the Spark side. Let's say these are my 256 gigs of RAM boxes, and these are 32 gigs. I'll run my Spark jobs on the bigger, beefier memory machines, and just run Cassandra on the smaller machines. That's workload planning. And so by using the data center awareness, and this is built into DataStax Enterprise, this is what it does. When you set up a Spark Analytics cluster, it creates a new data center for you. It just does that. So yes, you should be aware of it, but we manage it this way.
Okay. Next question. We have time for just a couple more. Yes.
You can group a number of time series together and give them a name.
Grouping a time. Give me an example.
So like in the temperatures, suppose you had 3 different ways of measuring temperature. Temperature 1, temperature 2, and temperature 3.
If it's in the
same.
same.
Always operate on, you've always needed those together.
Mm-hmm.
Would you
All right.
do that at the program level, or does the database support that?
Well, all right, so let's say that you're pre-calculating data like you stored in Celsius, Fahrenheit, and Kelvin. Was that okay? You would just store those, co-locate those. And so that data example that I gave you, the table that had temperature, is just one thing. You create temperature in C, temperature in F, temperature in K. And that would all be grouped in the same table. And because the clustering columns would be separate from that, it would co-locate all of those together. So it'd be those three data values would be always grouped together. So if you needed to say, give a year, month, day, and hour, and give me these 3 values, it would be the single seek on disk still.
So, follow up that. Can we have data as JSON or something like that?
Oh yes, we can. As of 2.1, we have support for limited support for JSON. 3.0 is going to be full support, but by that you have user-defined schema with collections, so you can have dynamic types. The part of it that is different from, say, like a document database like Couch or Mongo is it doesn't just take anything and deal with it. You have to define the schema first. We are still a schema database, and we will always be a schema database.
Next question. Yes.
What process does it have to go through if you add additional nodes to your cluster for rebalancing the data?
Good question. All right, so if I wanted to add, let's say I wanted to double this cluster right here, that is called a bootstrap operation. Very normal. It's actually in the Dynamo paper. It goes back that far. It's written in like the 10 Commandments, right? So whenever you bootstrap, you point it at one of the running nodes. It goes to that node, gets the cluster information, and then it also gossips out to the rest of the cluster saying, I'm joining, and that's one of the states. And by that, it says, here's my token range. And then all the other nodes say, oh, okay, that's your token range. I'm going to readjust mine. And then when that bootstrap operation, now all the other nodes say, oh, now that you're joining us, you can have some of our data because we're redistributed. So that joining process, the second part of that is the streaming, where it receives data from the other nodes. So what the ideal would be is if you double this cluster, each node would have half of the data that was already that they had originally, because they stream out. So they will not become online until they're in the up condition. So there's 4 states. There's joining, leaving, up, down. When they're up, then it's ready for reads. And it's very online. Yeah.
So a lot of the DataStax documentation says whenever a node is getting in or getting out, you should run a repair command. But the way you just said, it doesn't look like you need to run a repair command. But now documentation.
All right, so there's a repair and a cleanup. A repair operation is just a consistency check. So it's good housekeeping to do these things. Just like defragging your disk is a good idea. On a cleanup, you don't have to run it. You can just let it do it eventually. Those of you who are at OCD and probably in operations, like most of us, will run cleanup. And repair is done pretty quickly, too.
So it's recommended to run a repair command?
Right. You should run repair on your cluster every GC grace within 10 days.
Okay, next question. Yes.
More of a Spark question. If we have multiple data sources, let's say I have my data in Logstash, I have in Mongo, I have in all sorts of areas, and I want to do time series analysis post hoc using Cassandra. So what would be, will that be a relevant use case for Spark?
If you're collecting data from a lot, well, you can use a different connector, like there's a MySQL connector, I think, or you can just use, because it's Scala code, one of the evangelists on my team was actually writing like a MySQL, go get my MySQL data and bring it into Cassandra. It's like an ETL through Spark, because it's just a JDBC connection at that point. If you have that many data points and you need to collect them together, any best practice says you should try to find a place to, like one place for them to be.
I saw that last question of the night. Yes. No, you.
So I have a question. What would be the performance impact if, let's say, I was running all my Cassandra nodes on VMs with, let's say, like Ceph as a disk backend?
Wow, this is like the perfect last question. Now I can just get all pissed off. My good friends at Canonical tried to run Cassandra on Ceph. Didn't work. So let me tell you why. I just showed you the reason that disk makes sense, what we're trying to do on disk. Each seek means that's how many milliseconds it takes. If you're running Ceph, any shared file system has a network plug on it. You are instantly in the tens of milliseconds of latencies. If you have more than 20 milliseconds of latency on your storage, you will lose. It will just fall apart. And things like Ceph, NFS, even the high-performance SANs. I've got some of the best EMC SANs, IBM SANs. They fall apart because if you put that much load on them, the latencies start to go up. They're meant for random I/O, not sequential I/O. Don't do it. Simple as that.
Okay, Patrick will be here for one-on-one questions for the people who had their hands up and didn't get a chance. I apologize, but he will be here to answer the questions for one-on-one. Thank you very much, Patrick McFadin. Thank you all for coming.